Okay. All right, so the last thing I just want to do before we get on to pseudospectral methods for optimal control is just talk about the quadrature, the Gaussian quadrature weights. Gaussian quadrature weights. All right, I'm not going to derive these formulae. They are complicated to derive, so I'm just going to state them. First one is for Legendre-Gauss, the weights simplify to this. Wi is equal to 2 over 1 minus tau I squared times p n dot squared of tau I equals 1 up to n. For LGR, the weights are W1 is equal to 2 over n squared, and Wi is equal to 1 over 1 minus tau I times p n minus 1 dot of tau I squared. And this is for I equals 2 up to n. And then the last one is LGL, which is W1 is equal to Wn, which is equal to 2 over n times n minus 1, and Wi is equal to 2 over n times n minus 1 times p n minus 1 of tau I squared. And this is I equals 2 to n minus 1. Chalk sucks. Okay. Now, question that comes from all this is, we now have these three sets of Gaussian quadrature points: Legendre-Gauss, Legendre-Gauss-Radau, and Legendre-Gauss-Lobato. And let's go back to the optimal control problem for just a minute. But I'm not going to do the general optimal control problem because this gets very, very complicated very fast if I've got everything on the planet in there, okay? And nobody can see anything. So what we're going to do is we're going to derive direct collocation methods using Gaussian quadrature points. Now, the key thing about this is, like I said, if we do this for the general problem, the really complicated optimal control problem, which I started with, it's just going to get it's going to be too hard to follow. So we're going to use the following problem. And the reason we can do this is because everything else can be done once you understand this one. I mean, once you do this, the rest of it really is, there really isn't much of a change to it. So I'm just going to do this one, which is that we're going to have a Mayer cost. Well, first of all, before I do this, we're going to do the time interval is going to be from -1 to +1. So everything here is going to be done from -1 to +1. We're not going to go from T0 to TF because you can scale from T0 to TF -1 to 1 by simply doing an affine transformation. So the cost is going to be a Mayer cost, which is going to be x at +1. That's all we're going to have. The dynamics are going to be x dot equals f of x of t and u of t. And if you want to be really careful here, it's x dot of t. And I'm going to have an initial condition, x of -1 equals x0. Okay? Because once you can do this problem, like I said, you can extend it to any of the other problems. Now, the one thing that we normally do when we write vector equations is we assume all the vectors are column vectors, right? But in this derivation, I'm going to assume all the vectors are row vectors because it's easier to assume row vectors than it is column vectors. So x of t is going to be a row vector say this is true for u of t too, which is going to have the form x1 of t all the way up to xn of t. And you'll see in a little bit why it's just easier to do it this way. I mean, it's not the standard convention, but it makes these equations a lot easier to deal with. Okay. Now, back to Gaussian quadrature for a minute. So we've got these methods. We've got these Gaussian quadrature points. Now, if you remember, Legendre-Gauss includes neither of the endpoints, right? It doesn't include -1. It doesn't include +1. They're on the interior of the interval -1 to 1, right? Legendre-Gauss-Radau includes one endpoint, and Legendre-Gauss-Lobato includes both endpoints. Now take a look at this problem, just for a second. Tell me some things about this. This is why I simplified it down to this problem, so you could clearly see what's going on, all right? Or I should say it this way. You have a better chance to clearly see what's going on than you would in a general problem. What is going on in this problem? Explain what's going on in this problem. You know, one of the things about this class, it was funny because I was talking to somebody about this morning, is that you know this class is not a I tell you something, you go plug and chug. This class is a I discuss some things with you and you learn things, and hopefully if you have questions you come ask me and you get a better understanding of things. So part of that understanding is in the communication. And what is this problem telling me? So tell me what this problem is telling me. Describe this optimal control problem in words. Can anybody do this? Engineers don't use words, right? Engineers just use equations and numbers and stuff. That's so wrong. Words don't even describe how wrong that is, all right? No matter what you do in your life, you will have to communicate it. You better learn how to communicate well, because if you can't communicate, you're finished. Because the rest of it doesn't matter. You could have the greatest idea in the world, you could have the greatest result in the world. If you can't explain it to somebody, it's not going to make any bit of difference whatsoever. You're not going to be able to do anything with it. So tell me what this problem is telling me. Because I know what it's telling me. I just wrote it down. No one has any idea. We're all completely dumbfounded. Well, let me ask you one question. What quantities are involved in this problem? Well, that you should be able to tell me. They're all sitting on the board.
X and U.
What are X and U?
State vector, control.
And the control, right? It's the state and the control. What is happening now? What else is happening? So I've got a state and I've got a control. So in words, what is this problem telling me? What do I want to figure out?
The system vector starting at x naught, evolving, going by x dot.
Okay, I've got a set of dynamics that need this. I need to satisfy these dynamic constraints, right? And I have a boundary condition. This is an initial condition, but it's a boundary condition. Where is that boundary condition being applied? At time -1, right? And what's in my cost function?
The state vector
at time +1, right? What are -1 and +1?
Boundary conditions?
No, they're not boundary conditions. What are they?
Initial and final time.
They're an initial and final time, right? So, but now, let's go, now connect it back to this collocation over here. I just got through saying that Legendre-Gauss includes neither of the endpoints, right? Because the Gauss points are strictly on the interior of the interval -1 to 1, right? They don't include, I drew this picture the other day. It doesn't include -1, doesn't include +1. LGR includes one endpoint, but doesn't include the other endpoint, right? And LGL includes both endpoints. What do I have in this problem? Both endpoints, right? So if I'm a naive person, and I mean this naive, okay, because I'm going to show you in a bit that this doesn't work out this way. Which of these three sets of points would make the most sense to use? LGL, right? Of course, makes total sense, right? That includes both endpoints, right? -1 and 1 are in the set of collocation points, so it would make total sense that I would want to use that, right? So now let's do it. We're going to go backwards now. We're going to go, well, actually, we're not going to go backwards. We're going to go this way. I'm going to do LGL first, and then I'm going to do LG, and then I'm going to do LGR. All right. So, LGL pseudospectral method. Okay. Now, there's one rule. This is the rule. When you approximate the state, because we're going to do a state approximation, we're going to do this by collocation, you must use all of the quadrature points. You cannot omit any of them. And the reason is because you have to be able to use the quadrature points in order to be able to satisfy the quadrature rule. And the quadrature rule includes all of these points, right? So if you're doing integration, you're doing integration now by Gaussian quadrature. So whatever the quadrature rule is that you're using, you have to use all the points all the quadrature points, otherwise you're not using the quadrature rule, right? So you must use all the quadrature points. So the way we do this is we know that tau 1 through tau n are the LGL points. Okay? And tau 1 is equal to -1, and tau n is equal to +1. Okay, so now I got these points. Now, I'm going to do this with Lagrange polynomials. I'm going to interpolate the state using Lagrange polynomials. So what we're going to do is we're going to say that x of tau is going to be approximated by some function big X of tau, which is going to be the sum from I equals 1 up to n of x I Li of tau, where Li of tau is the Lagrange basis, which includes all of these points. Okay? And this goes for I equals 1 to n. Now that's my state approximation. So I'm approximating with this. Why am I using this for the approximation? Because you remember I told you one thing about Lagrange polynomials. This is what makes Lagrange polynomials so useful, is that the value, if I compute x of tau I, what do I get? If I evaluate this at one of these LGL points, what do I get? Let's look at the state approximation. What do I get? I get the sum from I equals 1 up to n of xi Li of tau j. Let's put a j here. Which is equal to what? What is Li of tau j? No, it's not equal to 1. When is it equal to 1? 0, except for what? It's not, what's that? Except for when I equals j, right? Li of tau j is equal to 0 if I is not equal to j. It's equal to 1 if I is equal to j, right? So there's no term in this summation that survives if I evaluate this at the jth LGL point, except for the one that corresponds to the jth Lagrange polynomial, in which case this is equal to 1, so this gives me xi. What this tells me is that this state approximation at the jth point is equal to the coefficient in that approximation, right? That's it. These coefficients are the values of the state approximation at that particular point, right? Oh, sorry, xj. Right, it's an xj. Yeah. Okay? So they are the values of the state approximation at that point. So now I have this state approximation. So now, what is the degree of this polynomial? Well, what are the degrees of these polynomials? How many factors do I have in the product? I'm going from j equals 1 to n, but j can't equal I. So I have n minus 1, right? So this is an n minus 1th degree polynomial, right? X of tau is a polynomial of degree n minus 1. Okay. Now what I'm going to do is I'm going to say, well, let's utilize that information to do this approximation now. Suppose I differentiate this. X dot of tau is equal to what? What's x dot of tau? Well, differentiate that. It's the sum from I equals 1 up to n of xi li dot of tau, right? I didn't ask you to take the derivative of the Lagrange polynomial. I asked you to differentiate that, right? Derivative of that Lagrange polynomial is a pain in the neck. It's got a huge product in it, right? It's a nuisance to do that. Now, let's suppose that I now am going to collocate. Remember, I have to use all the points. So I have to collocate it, all the LGL points, okay? So now what we're going to do is we're going to collocate the approximation or the derivative x dot of tau at the n LGL points. So what you get is you get x dot of tau j is equal to f of x of tau j u of tau j for j equals 1 to n. Right? I haven't done anything. I just collocate. But what's x dot of tau j? It's this thing evaluated at tau j, right? So it's equal to the sum from I equals 1 up to n xi times li dot of tau j, right? That's this thing. I just substituted it. And that has to equal f of x of tau j u of tau j. Problem is, do I have an approximation for the control? Did I write down any function approximation for the control? I didn't. So there is no function u of tau j. This does not exist. This is wrong. What I have is I have a value of the control at that point. That's all I have. So this is actually more correctly stated as f of x of tau j and uj, where uj is not the value of the function approximation to the control at the jth point. It's just a value of a control at the jth point, because I don't have any underlying polynomial or any other kind of approximation for the control. I don't know anything about the control other than I'm sampling it at these NLGL points. That's the only thing I know, whereas I do have an approximation for the state. But what is x of tau j? We just went through this. What is x of tau j? It's xj, right? xj u j. Now, this says that this thing is true. So let's suppose I take this matrix now, because I'm going to get a matrix. This is why I'm using row vectors, by the way. You'll see in just a second that it makes a lot more sense. Suppose we say let dij equal li dot of tau j. Dij. Yeah, doesn't matter which way you do it. But, so what do we get here? We get the sum from I equals 1 up to n of dij xi is equal to f of xj uj. I'm going to flip these this way. Okay. So this thing here, if I was to string this whole thing out into a bunch of equations, what I would get is a set of matrix equations that looks like this. I would get d11, d12, all the way up to d1n, d21, d22, all the way up to d2n, and this thing would go down to dnn. This thing would go down to dn1, like this. And what I would get, because I'm treating the state as row vectors, I would get x1 all the way down to xn. n. And the only reason I can do that is because if I had treated these as column vectors, I couldn't do this matrix multiplication the way I'm doing it, but these are row vectors. So the math works out exactly the way I've got it, which is why I decided to use row vectors. This is equal to, using a shorthand, f1 all the way to fn, where fi is equal to f, or fj is equal to f of xj and uj. Okay? Now, look at that system of equations. How many equations do I have? How many vector equations do I have? Make it easy on yourself. If you don't like that, you can use that last equation I've got over there. How many vector equations do I have here? Yeah. Right? I've got n vector equations. I really have a total of big N times little n, where little n is the number of states, right? So it's the dimension of the state equations. But if I just stick with vector equations, I have n of them. Now, that means what's the size of this matrix? Well, what's the size of this matrix? It's n by n, right? This is an n by n matrix. This is n by 1. And this is n by 1. Okay. Now, well, it looks good, doesn't it? Looks really nice and simple. It's nice and clean. It includes the boundary points. So now let's add to it the Mayer cost and this initial condition. So because x of minus 1 has to equal x0, that means that if I discretize this, I get x1 equals little x0, right? Because the value of the state approximation at -1 is equal to the first value in this approximation, right? Because it's I equals 1, which is the value at -1, which corresponds to capital X of 1, right? So this is my discretized initial condition. So don't fool yourself here into thinking that, well, this is the same thing as this. This is not the same thing as this. This is the state at -1 equals x0. This is the state approximation at -1 equals x0. All right? They're two different things. This is a discrete approximation to that. The Mayer cost, I know that phi of x of plus 1 has to equal what? Is replaced. I should put a replacement here. Is replaced by phi of capital X n, right? Because x at plus 1 is approximated by capital X at plus 1, which is equal to capital Xn, right? So I have this optimization problem now. I'm gonna do a little bit of manipulation here to make these things a little bit easier to deal with. But it looks like this: is that suppose we say let capital X 1 to n equal x1 up to xn, and we say u of 1 to n equals u1 up to un, then what I get is we get the following NLP, which is D, which is that whole matrix D over there, times x of 1 colon n minus f of 1 colon n, where f of 1 colon n is this whole thing evaluated at 1 colon n, has to equal 0, right? And I've got the cost function that I'm trying to minimize, so it's minimize phi of x n subject to this and the condition that x1 minus, oh, I should write this correctly. Put this over here. x1 minus x0 has to equal 0. So I'm trying to minimize this cost function subject to all these constraints. Now that looks like a pretty simple system. And it looks a lot like the system that we started with, right? Because the system that we started with, the optimal control problem, was this. And that looks a lot like that does, doesn't it? Right? It just looks like a discrete equivalent. Now, here's where the problem comes in with Lobato points. When we're solving this optimal control problem, what do we need to do with these dynamics? We need to integrate them, right? So if I want to integrate, integration means that I have to have a way of being able to accumulate essentially the area under the curve. But these equations over here don't look like they're in integral form, do they? They look like they're in derivative form, right? The derivative of something, approximation, minus something equals 0, which is what I've got over here. But the difference is when I'm done solving this problem, I'm going to wind up having to integrate these equations, which means I've got to have some way of being able to integrate or do some approximation to integrate, right? Well, I just got through talking about Gaussian quadrature. Gaussian quadrature is a way to integrate, right? But this is not an integral form. In order for this thing to be an integral form, what I would need for integral form is I would need this. So for an integrator, or for integral form, using LGL points, we'd need the following. We'd need that the state approximation at any one of these points has to equal the initial value, which is x1, plus some quadrature approximation, which I'll call it alpha ji times fi. Where, if you look at this, all I've done is I've just said, well, I'm going to approximate the state at every single point, every single LGL point, as the initial condition plus some set of quadrature weights that correspond to that particular point. This is equivalent, or what I'm trying to do is I'm trying to make this equivalent to the following statement, which is that x of tau has to equal, if you want to be more careful, x of tau j has to equal x of minus 1 plus the integral from minus 1 to tau j of f of x of s u of s ds. And what I've done is I've said, well, x of negative 1 is equal to this, right? So I'm approximating that. And then I'm going to approximate this by some sort of a quadrature, right? Well, what quadrature am I going to use? I'm going to use the same quadrature I used to establish the set of points I've chosen, which are the LGL points. So this would have to be an LGL quadrature, which is why I sum from I equals 1 to n. So these points, these here, are the quadrature weights that integrate me from minus 1 to tau j. There's nothing actually fancy about this, because if you look at this, you can actually compute what those quadrature weights are in terms of the original LGL weights. So the way you do that is as follows, which is that let's suppose that I say that I take this interval. I say S goes between what? Negative 1 and tau j, right? Which means what? So if I'm gonna like do this in a slightly different form, I'm going to get 0 is less than or equal to s plus 1, which is less than or equal to tau j plus 1, right? Now, if you divide this by tau j plus 1, you get 0 is less than or equal to s plus 1 all divided by tau j plus 1, which is less than or equal to 1. So if I continue that over here, I get 0 is less than or equal to 2 times s plus 1, all divided by tau j plus 1. And then that's less than or equal to 2, which means that negative 1 is less than or equal to 2 times s plus 1, tau j plus 1, which is less than or equal to 1. So what I can do is I can replace this, right, with the following approximation. I can say that if you look at this, you say that, well, that says that this quantity right here, call this new variable, call it q, right? So let q equal 2 times s plus 1 over tau j plus 1. There's a minus 1. Okay? So that means that dq is equal to what? It's equal to 2 over tau j plus 1 ds, right? So if I replace that over here, I get the integral from negative 1 to tau j of f of x of s u of s ds can be replaced by what? Tau j plus 1 over 2 times the integral from minus 1 to plus 1 of f of x of q u of q dq. I haven't done anything. I just did a transformation. It's an affine transformation that takes me over there. So I know what the weights are, the LGL weights are on negative 1 to 1, right? I wrote them down on the board at the beginning. So these values, alpha I, alpha ji, are going to be the weights associated with this thing, tau j, right? Because I know that I can approximate this by an LGL quadrature, right? So this whole thing here, can be approximated by the standard LGL quadrature, which is the sum of wi fi for I equals 1 to n. So now what I'm going to do is I'm just going to multiply the whole thing by tau j plus 1 over 2. So alpha ji is going to equal tau j plus 1 over 2 times wi, where wi is the LGL weight. Okay? Now, that's if I was doing this in integral form. That's what I would need to do if I was going to integrate this. And what I would get here is I would get xj, let's rewrite this equation, is equal to x1 plus the sum from I equals 1 up to n of alpha ji fi. Now, now I have a new matrix over here, right? I've got this matrix of alphas, right? So if I take this matrix of alphas, I can string those out into a matrix like this. Alpha 1, 1, alpha 1n, alpha n1, alpha n. Now, if I want this system to look like that system, or sorry, maybe do it the other way around. If I want this system to look like that system, how would I get them to be equivalent to one another? Because what I'm going to get here when I'm all done is I'm going to get x 1 colon n is going to equal x1 times a column vector of 1s. That's a column vector of 1s, right? Plus, call this matrix A. A times f1 colon n. Where literally I mean that. This is literally just a column vector of 1s. Again, this is why I'm using row vectors. It makes the math work out if you use row vectors. Okay, so did I do that right? No, sorry, this is wrong. This is a 1 still, but it's 1 times x1. Okay. Now, if I want that system over there, let's put it beside the other system. So remember the other system. I don't have any room here. I'll put it over here. So if I want to write this as an integrator, then somehow I need to manipulate this system. D times x 1 colon n minus f of 1 colon n equals 0. I need to make this look like that. How am I going to make that look like that? Well, first of all, you notice that I have this initial condition sitting here, right? I don't have another term in these equations. I only have 2 terms in this equation over here. I have 3 over here, right? So what I could do is I could say, well, one thing I could do is if I could invert D, I could get this to kind of look like that, right? So suppose D was invertible. Suppose D inverse exists. Then I can multiply the whole thing through by D inverse, and I get x 1 colon n is equal to D inverse times f of 1 colon n. Well, that kind of looks like that, right? Except for it's missing one thing. What's it missing? Missing this first term over here, right? Now, what else is true about this matrix that would make it so that this is not, that I can't get this to do this, even if D inverse existed. But now let's look at this matrix, and let's look at the D matrix. So let's go back to the basics, all right? Which is, if you remember, the state approximation is a polynomial of degree n minus 1. So that means this derivative approximation is what? of degree what? N minus 2. How many equations do I have over here? How many vector equations? N. I have capital N. How many coefficients, vector coefficients, do I need to uniquely define a polynomial of degree n minus 2? N minus 1, right? This is uniquely defined by n minus 1 vector coefficients. But how many equations do I have there? N. So do I have more equations than I need to define this derivative polynomial or less? More. Which means what's true about this system over here? It's overdetermined, right? It has to be overdetermined because I cannot find another coefficient to help me uniquely define this polynomial because it's already been uniquely defined by n minus 1 coefficients. Adding another coefficient is not going to add any more information than I already have. I need n minus 1 coefficients to uniquely define this polynomial. So I have an overdetermined system, which means what has to be true about this matrix? It's an overdetermined system. It's singular, right? So this means that D is singular, which means D inverse does not exist. So even if I wanted to invert this system to get it to kind of look like what I had in this system over here, I can't do it because D inverse doesn't exist. It's not invertible, which means that the LGL method is not a Gaussian quadrature. It's not a quadrature method. It's not a quadrature method. In other words, quadrature is a way of approximating the integral of a function, right? But this doesn't approximate the integral of a function. It doesn't approximate the integral of the state, which is what you want it to do, because when you're all done, you want to be able to solve the problem by integration or by some method of integration or numerical integration. You're not doing numerical integration. In this method, the only thing you're doing is differentiation. Now, this is something that gets to another fundamental point, which I don't think a lot of you ever think of, and most people don't think of this, so don't feel bad about this. But think of it in a more sort of, in a more calculus kind of way. If I have a function, f of t, and I have another function, g of t, can two functions have the same derivative? Sure. Under what conditions? When can two functions have the same derivative? I'm talking about total derivative here. I'm not dealing with partial derivatives. So, if I have f of t and g of t, and I say df dt and dg of t are equal to each other, right? Then what can be true about f of t and g of t? What's that? No, it has nothing to do with powers.
They're the equal or constant.
What's that? No? Here, I'll give you a hint. Suppose I give you the function f of t equals t squared plus 5, and f of t equals t squared plus 3. Do they have the same derivative? What's the difference between them? They differ by a constant, right? So any two functions, as long as they differ by a constant, will have the same derivative, right? So what this is saying is that differentiation matrix, so what does it tell you about derivatives? What's true about the derivative operator? So if I take the operator d by dt, you don't think of it this way. What is true about the operator d by dt? You just told me that matrix D is singular. What's true about this operator? No. What is it? What's true about the differentiation operator? Look what I've got here. Suppose I've got a function. Let's say f of t is equal to g of t plus a constant. If I take df dt, I get dg dt. What happened to the constant? Why? What happened? Where'd it go? Why isn't it there? Why isn't it here? It should be, right? What's dk dt? Why? It's not a function of t, right? So its derivative is 0. What does that tell me about the operator d dt? You don't think of it this way. This is why you're having trouble with this, because you've never had to think of it this way. You just told me that matrix D was singular. What does it mean for a matrix to be singular? Let me go back to that. What does it mean for a matrix to be singular? It's not full rank, right? What's another way of saying it?
Its rows or columns are linear.
Yeah, it's the same thing. It's not full rank. What else? What else is true about it?
It's a non-zero null space.
It has a non-zero null space. Now I'm starting to think like PhD students, all right? What does it mean for something to have a non-zero null space? What does it mean for something to have a null space? Wait, non-zero null space, it's the same thing, a null space. What's the definition of a null space? Of a linear operator?
Set of vectors such that A, the matrix, or the operator times the vector.
It's 0. Okay, so what do I got here?
A non-zero vector.
I've got a non-zero function, right, in this case, right? Because I'm dealing with a function space, not with a finite dimensional vector space anymore. But if I take the derivative of a constant, I get 0, right? Which means that constant, or any constant, has to lie in the null space of this operator, right? Because the derivative operator is a linear operator, right? If I take the derivative of a linear combination of functions, I get the linear combination of the derivatives, right? So this is a linear operator, which means that this constant lies in the null space of this linear operator, which is completely consistent with what I did over there, right? I constructed this matrix D purely out of differentiation using all of these Lobato points, and even though Lobato points look like a perfectly normal thing to use because they include both endpoints, I wind up with a singular differentiation matrix, so this method doesn't do integration. It does differentiation. This is a derivative method that has no equivalent integral form because I can't invert it to get it into a form of a quadrature. This is the form I would get if I was doing it as a quadrature rule, right? Because this is the quadrature rule. But this matrix D is singular, and as a consequence, cannot be inverted, and it can't be put into the form of this quadrature. So it's not an integration method. So this method looks beautiful on paper. It looks great. You're like, oh, wow, everything worked out so nicely. I get this simple system of equations I get to evaluate. And in the end, I'm not doing integration, which is what you need to do in order to solve the optimal control problem, because you need to integrate that differential equation. So you just constructed a method that doesn't do integration. And this comes along with it a whole host of other problems, which I don't have time to go into today. I'll go into it after I've derived the other methods. So the LGL method fundamentally has a flaw in it, that it's not an integration scheme. All of the other methods that I've talked to you about so far are integration schemes. Euler, Runge-Kutta, if you extend that midpoint rule, trapezoid rule, Hermite-Simpson, any of those methods are all integration schemes. They're all implicit integration schemes. They approximate the solution to the differential equation by quadrature. They're not accurate quadratures, they're low-order quadratures, but they nevertheless are quadrature rules. So even though in the Euler method it looks like you're doing differentiation, you remember in the Euler method, this is the last thing I'm going to write down before we quit class today, because this works perfectly fine for Euler even though it's not very accurate. You remember we got something that looked like this in Euler. We get xk plus 1 minus xk all divided by h is equal to fk. Well, that looks like a derivative method, right? But you remember that I can rewrite this as xk plus 1 is equal to xk plus h times fk. This is an integration scheme, right? This is the same thing as that, because I can algebraically manipulate that into this form over here, right? So I'm doing integration even though it looks like I'm doing differentiation, right? So this is a derivative method which has an equivalent integration scheme associated with it, which means it's an implicit integration scheme, which means it's a quadrature rule. It's not a very good quadrature rule. It's a very inaccurate quadrature rule. But nevertheless, it is a quadrature rule. It's basically your rectangular rule, right? That's all it is. But it can be written in either form without any loss or any destruction of information. This method over here, if I start on the derivative side and I do everything with differentiation, I lose information because look what I've lost. This matrix is singular, so anything that lies in the null space of this matrix gets lost in this equation. If I multiply D by some vector, and there's a component of that vector that lies in the null space of D, it's going to get annihilated by D, right? So there's something in this system that could get lost in the process of doing the calculation, right? Because if it lies in the null space of the matrix D, I'm done for. I can't recover it because it's in the null space, right? In this case, I don't have that problem, right? Because this doesn't have a null space associated with it. Because this system can be written as an integrator, so there is no null space. So it's weird. I've got this set of quadrature points that includes the endpoints, which naturally allows me to be able to write everything in this nice, clean way where I keep track of all the endpoints perfectly, but I have a null space in that operator, which completely obliterates all the work I just did to construct this method. So LGL, as a set of quadrature points, don't work from the standpoint of Gaussian quadrature, or any quadrature. They're not a quadrature. Yes?
We add the boundary condition to that equation. I would consider both equations together. Do we still have the null space?
Yeah, you still have the null space. You mean this one plus this one?
Yeah.
Well, this one can't add any information to this because how many this already includes this over here. Now I have, well, now how many equations do I have if I add this?
We still have the same number of equations.
No, I've got n plus 1 now.
Oh, yes.
I've got another, I've just made the situation worse,
Yeah.
right? Because I have n, I've added another equation. So I haven't even considered the initial condition yet, right? If you consider the initial condition in this system, now you have n plus 1 equations, right? But you haven't helped yourself at all because this is fixed, right? So I've actually taken out, if I take out one of these elements, I take out one of these, it doesn't make a difference. I wind up now with one less equation, but I wind up with one fewer unknowns too, so I still wind up with a singular system, right? So I can't get rid of the singularity. The singularity is still there. Okay, so Monday, we're going to talk about Gauss. We're going to go through all the details with the Gauss pseudospectral method, and I'm going to show you counterintuitive. It's counterintuitive at first when you do this with Gauss, and it looks like there's no way in the world it could work out with Gauss. And the main reason it looks counterintuitive is because the Gauss quadrature points don't include either of the endpoints. You say, well, how am I going to put the boundary conditions properly if I don't have the endpoints in the quadrature, right? The quadrature includes tau 1 through tau n, but tau 1 is greater than -1 and tau n is less than +1. So if I just use the Gauss quadrature points, even if I tried to use them, I would not be enforcing the boundary conditions at the right points, right? So Monday I'm going to show you how you actually use the Gauss quadrature in the proper way to be able to account for the boundary conditions, and you actually get all of the information, even though it looks at first like you don't have it. You actually do have it. We'll go through that next lecture.